Hello, in last session we learned about random access memory. Using your random access memory, how to load the data, how to retrieve the data. So using your memory read and memory write operation, we learned it. But here in this session, so how the chips are selected or how the memory devices are selected, how the binary cell can hold the data, and how it retrieves your data from that binary cells. So those are all the decoding techniques of your memory we're going to learn in this session. Now, so in order to decode your memory, so first let me learn about, so what is a binary cell? So how many number of inputs are there? So binary cell is nothing but a flip-flop, basic flip-flop, which can hold only one bit of data. So now here each memory word can have a collection of binary cells. Based on that collection of binary cells, you can have your data bits, which you can load into the memory word, or you can retrieve your already stored data through that binary cell. Now hence here binary cell can have your three inputs and one output. These three inputs are select input as well as your data input, and one input, the third input or the last input is your read write control input. And the fourth one will be your data output line. So this is a simple block diagram of your binary cell. Now let me learn about, so in detail about your binary cell, what will be the inside logic of your binary cell. So this binary cell is constructed in a static RAM using your flip-flops. So a flip-flop is the one which can hold one bit of data based on your inputs as well as your previous state. Now in order to select your a particular binary cell, so using your decoder, address decoder, we are going to select that particular binary cell. So hence, so this select input is transferred as the inputs of your AND gate 1, the inputs of your AND gate 1, these two first and second AND gates are the input gates, and this is third AND gate is the output gate. So this select input is transferred as one of the input of your first AND gate, second AND gate, along with your one of the input of your third AND gate. So select inputs are is equal to 1 1. So all are 1 1. If it is binary cell or the memory word is selected, then select line will become logic 1, and they are applied onto the input of your first AND gate, second AND gate to become logical 1, as along with third AND gate is also equal to logic 1. So now based on your control inputs, read or write, so you can have your data which is retrieved from this binary cell, or you can load the data into the binary cell. For example, now if I wanted to load the data, so then I need to apply a control signal which is 0 on your read or write bar. So when I apply a 0 on your control input, so simply it can store the data. So now I wanted to load a logical one, so hence I will transfer the logic 1 input data through this data input line, Now if I transfer this data input line, it has been applied as one of the input on your first AND gate, and complemented data input is applied onto the second AND gate. Since complemented input as I gave 1, so hence it is 0. So second AND gate will give you the output 0. First AND gate output is decided based on your read signal. So read or write bar is 0. So this 0 is complemented as logic 1. Hence this logical one output of a NOT gate is applied as one of the input of first AND gate and second AND gate. So now here, so data input is complemented, is connected to the second AND gate. So it will give you the 0 output. Since here 3 inputs are 1, since first AND gate will give you the output of 1. So now so these are two AND gates outputs are being transferred as your set input and reset input. As read or write bar is 0, so this becomes the one of the input of the third AND gate. So 0 is applied. So now, so set input become 1, so reset input becomes 0. So state of the flip-flop now it will be equal to logic 1. So since your read or write, so you are just loading the data into the flip-flop. So based on your input, now my input is 1, So hence this flip-flop is loaded with 1. So now output should not be, so we are not reading the data, hence it will give you the 0 output because my write signal is 0. So we loaded the data. Now when I wanted to read the data, so then my control input must be enabled with logic 1. If I enable my control input with logical 1, already my output of this SR flip-flop earlier it is loaded with logic 1 through your data input. Now if I wanted to retrieve the data, so then I need to enable this read signal is equal to logic 1. When read signal is logic 1, it is complemented as 0, and this 0 is applied onto this input of first NAND gate as well as your second NAND gate. So if one of the input of your first NAND gate and second NAND gates are 0 0, so S input is 0 as well as your R input becomes 0. So since my AND gate one of the input is 0, so though your select input is 1, okay, or your input data is under it is 1, so it will give you the 0 outputs on your first AND gate and your second AND gate. So SR inputs are 0 0. There is no change operation is performed. So the flip-flop may not change its next state. So it continues your next state as your present state. So present state is 1. So earlier I loaded 1. So that will be transferred as 1. So and select input is 1. So now here read is 1. So hence output will give you the logic 1. So now select input is 1, read input is 1. If you are storing earlier with a 0 data input, that 0 data input only transferred as your one of the input of your third AND gate. So as at your output gate, so it should have your 0 output. So like this, data is loaded or data is retrieved from your each binary cell upon selecting and enabling a control input and inputting your data with a particular data input of 1 or 0. So you can obtain your output from each binary cell. But in order to decode these all the things, so we need to go for the memory decoding. Now this memory decoding is constructed using a simple decoder of 2x4. We have constructed a 4x4 RAM. So where this the first digit indicates your number of memory words. So now I can write this 4 as 2 power 2. So 2 power 2 indicates, so in order to decode your one of the memory words, so I require 2 address bits, and those 2 address bits are A1, the one is A0. So now first we have to select your memory. So for the purpose we are just using the memory enable. So that memory enable is transferred as your enable input of your decoder. So hence this decoder is switched into on state. If your memory enable is 1, so if it is 0, so this enable becomes 0. So this decoder will become off. No data is loaded or no data will be retrieved from your memory. So hence here when enable is 1, so memory enable is 1, that is transferred as your enable input. When enable input is transferred, so decoder will become switched into on state. When it is switched into on state and based on your address inputs, so it will select one of the bit. For example, now I have selected a first address, okay, or let I take this is a 10. So 10 means second memory word. So this memory word, second memory word is selected. So because of my address input is, let I take this 10 as my current address input. So now since I applied 10 on your address input, so word 2 is selected and that word 2 is connected with this 4 binary cells. So as here the second data, so the second number is indicating your data bits available on each memory word. So since that we have here 4 binary cells, where these 4 binary cells are having 3 inputs. So first one will be the select input, which comes from the, so select input, all the 4 binary cells are connected to that memory word. So since memory word 2 is selected, so all the select inputs of each binary cell is equal to logic 1. So since that these 4 binary cells are selected, now based on read or write. So if I enable read equal to 1, so then this read control input is connected to this. So as we are one of the input, second input. So since that, so if a read control is enabled and select input is enabled, our select input is selecting a particular binary word. So from the output terminal, the loaded data is transferred through this OR gates as your data input. So as your here data input D0, D1, D2, D3, we obtain that 4 data bits from which binary cell. For example, if I wanted to have a memory write operation upon selecting a memory word, so let I transfer a 0 on your write bar, read or write bar. So then write bar is enabled on this. So when this write bar is enabled, so it will provide your a path through your input data lines, and hence that input data lines as I0, I1, here I2, I3, that particular data input is loaded. For example, I wanted to load a data of 1011. So hence I will transfer I0 is 1, I1 is 0, I2 is 1, I3 is 1 are to be loaded into the binary cell. So upon again enabling your read can read out the data through this OR gate outputs. So OR gate outputs will give you the data bits, and these parallel inputs will provide your data inputs, so which is loaded into the each binary cell upon selecting your memory word using your address decoder. So like this, so we can read the data or we can write the data into the RAM. So using the memory decoding, and so in order to have this designing, so we require, so since the previous example is a 4x4 RAM, so only we used a very low order decoder which is 2x4 decoder. But if you come to your large memories, so then you require, so if it is having a k number of address line, you have your 2 power k number of words are available with the n bits per each word. So the order of the decoder required must be equal to k into 2 power k. So this is the order of the decoder. So in order to obtain this type of decoder with a high order, so the cost of the memory device is very high. So hence in order to avoid that, we are moving to the other method called as coincident decoding. In this coincident decoding, instead of taking this k, so k number of inputs, so let me divide that k with a k by 2. So now, so using this coincident decoding, so let me divide your number of address bits, so with a half. So now for example, now, so let I take a 10 number of address bits. So now 10 is divided by 2 means, so 5. So if I use the 10 number of address, then now the order of the decoder must be 10 into 1024 words. So 1024. So 10 into 2 power 10. So that size decoder we have to take it. So now in your coincident decoding, let me divide this number of address bits into by 2. So then we have here 5. So then we can prefer your 2 number of 5 into 32. So 2 number of 5 into 30. Instead of taking 10 into 1024, which is a very high order decoder. So let me divide your number of address bits with a 2. So half of that. So then we have the 2 number of decoders which are of the order of 5 into 32. So now using that 5 into 32 decoders, so we can form a two-dimensional array. So first decoder will give you this is your row decoder, and this will become the column decoder. Each coincidentally, where your memory locations are coincident. So for example, this is your 00 location. So we can obtain here this coincident dots from this coincident dots we will obtain your total number of locations are 1024. So your 1k word or 1 kilo word memory is designed using a two-dimensional decoding with a low order. Instead of taking 10 into 1024 decoder, let me divide that into 5 into 32, and each outputs let me take as a row 1. Another one will be your column 1. So the most significant bits of your address is applied to the X decoder, and the least significant 5 bits are applied to the column decoder. Now in order to select this, so 0, 1, 1, 0, 0, so 12th one. So wherever the 12th row is coincident with your 28th column, So that become the address of your 01100101010. So like this we can avoid that bigger or the higher order decoders into using your low order decoder using the coincident decoding. Next, so here in order to avoid the number of address bits, so for example, if I have 16 number of address bits, so then in an IC, so if I'm using a processor, so I require that 16 number of pins only dedicated to that address bits only. Instead of that, what we are going to do is here we will also divide your address bits into by two. So as we have two address bits, we'll separate that or divide that address bits into two. So then, so we can use here. So one of the address is applied to the row register, other one is applied to the column register. So with that we can obtain your 1024 or your, so 64 kilo is total is 2 power 8 is 64 into 2 power 10, sorry 2 power 6 is 64 into 2 power 10, so which is total 2 power 16. So instead of having 16 number of address lines, so let me divide this 16 number of address lines into 2. Then we have here 8 number of address lines. So using this 8 number of address lines, first we will transfer the lower significant address lines to your 8-bit register, through your 8-bit register to the row register. Upon enabling your CAS column address register, so then the next 8-bit registers are transferred to the 8-bit column register, and here the decoders which are used is 8 into 2 power 8, 2 power 256 decoder, 8 into 256 decoder we are going to use. So now using your coincident decoding we can obtain total 64 kilogram. So now in your dynamic RAM, so when I am comparing with the static RAM, so these dynamic RAMs are having the 4 times the denser than your static RAM. Static RAM is consists on only the flip flops. So flip flops can have your connection of your FETs. So whereas your dynamic RAM is obtained, each cell is obtained using your one capacitor. So hence they are 4 times. But here if I use that 16 number of address lines on your IC, so in your IC package only that 16 pins are dedicated to that address bits. So in order to avoid that, we are going to divide that address bits into 2, and then we are going to minimize that address inputs required are 8. So with that, same set of pins are used for both parts of your address, and this package which you require is decreased significantly. So like this, using your address multiplexing, so we were going to decrease the IC pins required on your chip. So this is the today's session. Next session we are going to learn about the ROM.